UTS Canvas?
Yes.
Yeah. Cool. So today's lab, we put into the modules week 3 here. So basically today we're gonna ask you to do MATLAB, both MATLAB and LabVIEW exercises. First, how to import data, the signal that you collected or you downloaded last time in the week 2 lab. Import data into MATLAB or LabVIEW, how to do a simple segmentation of the signal, then how to do FFT. And if we have time, you can start to work on the digital filters. But yeah, there are in the canvas, we gave you some functions, load functions, save and load, import tools. Those are very helpful links that you can have a look. I think some of you should have already read those things because we post this very early of this semester. So and FFT here as well. So now I just want to do a little bit of demonstration on how to do how to import signal into MATLAB. So now we have MATLAB here. I just share the screen. So the signal that you collected last week would be something very similar to this. Right? TDMS file named as EMG test 02. So if I double click, you will see the Excel opening this TDMS file. Most of these informations are not that important. Only thing you need to pay attention is this WF increment. This showing at 0.002. That means from one sample to another sample, the time increment is 0.002 seconds. So that means your sampling frequency should be 500 Hertz. And over here, you have biosignal that's in the second sheet. That this is the signal that you have actually collected. In Excel, there's a quick way to check it, whether you have a valid EMG or ECG signal. So you go to Insert, and you simply just plot this 2D line chart, and you have this sort of EMG graph that you can see. Since there's a lot of sample in there, it can be a bit of lagging. So don't worry too much on how to plot using Excel. We just use Excel here to import data. We're not going to do any coding or anything using Excel in this subject. So once you have that, we go back to MATLAB, and there are a number of ways to import signal from Excel or TDMS file to MATLAB. One quick way I did is, firstly, I will need to save this. So in here, save as anywhere you want. So we just save it at MATLAB here. So we want to save it in some format that is not TDMS, because MATLAB cannot directly read from TDMS. So we just save it at Excel workbook. That should be fine. I already actually saved one here. So I named it as EMG sample 0.1. So if I open this file, it would be exactly same as what we had before. So it will be exactly same as we had before. So this is the specification of our saved data, and this is our biosignal. Once we have that, we go to Home, and there's one app called Import Data. Just left-click Import Data. It will ask you what file it should read, and we just go to MATLAB. This is where we save. So it's called EMG sample 01. Double-click it, and this comes up when down reading it. We don't really need anything here to import, so we just go straight to biosignal here, and it automatically recognizes this column of data from 2 all the way to A31351. So it's quite a huge file. It has a lot of samples in it, and we can choose the data output, the output type. It can be table. Can you see?
Yeah.
Yeah.
Yeah. So it can be table, can be column vectors, numerical matrix, or anything. So I think one easy way is numerical matrix. So if you click that, we just import selection, import data. And in your Matlab, sorry, there's a lot of things. Let's just clear everything. CLC, we do it one more time. Numerical matrix input, then this will show up. So this is the data that if we open, double click it, and this is the data that we acquired from the NI device. Now, if we open a new script, so I believe all of you should know how to start a new script just simply by clicking that and save in your computer. The first few lines, CLC clear, close all, that's the first line is clear command window, clear the variables and close all the figures and stuff. And you write your comments to let everyone know what you are going to do. So the first part is loading the collected data. We have already imported here at EMG sample 01S1. So we just load. So okay, the next thing is what we do is we right click this and we save as. And we save as a .mat file. I already saved as EMG sample, so that EMG sample.mat file is here. So all we need to do is type one simple command called load EMG sample .mat. Then if we run this section, and let's just comment on the rest of this. So if we just run this section, we will have our EMG sample 0.1 here. And this is a quite tricky name. So what I did is I just renamed it. I set a section called initialize variables. So I can initialize all my variables in this section. If I need future variables, like more variables in the future, I can always initialize here. So the first variable I named as raw data. So the raw data is exactly the same thing that what I have just loaded. So if I run all this, I have a new variable called raw data, and it's exactly the same as the EMG sample 0.01S1. Now, if we want to simply plot it, to just look at it, I just put figure 1. That means it is the first figure that my script will generate, and it's just simply plot raw data. If you click that, you will see this window where you have all of your data plotted out. It's important for any data that any figure that you plotted. It's important you have your title, your y-axis, your x-axis. So this is a very bad example of plotting a data. So when you actually write your own data, when you actually write your own code, and especially when you try to write your report, submit your report, don't put this thing in your report. It will definitely you will definitely lose some mark here. All right, so to put x-axis and y-axis in. It's simply x label, y label, and title. You will see those commands later. All right. So now you have a figure looking like that, but you can see there's a lot of signal going in here. You have a lot of EMG envelopes in here. It's a bit hard for you to do filtering or FFT for all of them at once and see what's exactly in there. So it is a good habit to kind of make the signal into a smaller pieces. So the next step, which is called segmentation, we just put a smaller pieces, we get a smaller pieces of the signal for analysis purposes. So we have data seg1. So that's the first segment of the data. I chose from the index 1501. This is because since our sampling frequency is 500 hertz, so we have 500 samples in 1 second. That 1500 divided by 500 gives us 3. Then we manually remove the first 3 seconds. Most of the times we remove the start of the long collected signal because we assume that participants weren't ready and would introduce a lot of noise at the very beginning of the collection. So we sort of manually remove the first 3 or first 5 seconds of the collection. In this case, I removed the first 3 seconds. So from here, I go all the way up to number 2500 sample. That means the 5th second. So in this data seg 01, we have exactly 2 seconds in there. So if we run this, we don't really need to see that anymore. So if we run this, we'll see a new variable called dataseg01. If we simply plot it and right click it, we can see this is the first from the 3rd second to the 5th seconds of the EMG signal, which is a bit clear for us to see what is exactly going on in here. But again, the x-axis is sample, number of samples, not time. So this unit is not time. And the y-axis should be microvolts. Okay, so next step, we want to do an FFT. So for MATLAB FFT, I think there's a very good example here. I already put the link on Canvas, so all of you can have a look. It's a quite simple function, just type FFT and X in here. This is the example. I already put this example into MATLAB, so we can have a look over here. So we have CLC clear close all. That means we get rid of all these variables, whatever we have in the command window and whatever figures that we generated before. First thing, in that example, we have a sampling frequency fs, which is 1000. That means it's 1000 hertz sampling frequency. Next line of code is called capital T equals to 1 over fs. That's the sampling period, which is 0.01. It's very similar to the WF increment that we had in our Excel file, the TDMS file. The length here, the length of signal in this example, it gives us the exact number, 1500. But in most of the cases, since we don't want too many constant in our code, so it's a good one good way to do it is you use L equals to probably right here. L equals to length. So this length function is keep returning the length of the array, which is array A. In this case here, we put length data seg1. That's this will automatically generate the length instead of using any constant. So it's also a good habit to write less constant and more functions in your script, so it wouldn't create much of a problem when you are running some other testing samples in your for your script. Next is T, which is time vector. Since we have our capital T equals to 0.001 here, and our total length is 1500, then our T starting from time 0 seconds all the way to there, and it's sort of divided by 1000 or times 0.001. That gives our time vector, which is the, you can think of as the x-axis of your time plot. Any problems so far? Should sampling frequency for our case be 500? Yes, it should be 500 hertz if you are collecting your signal from our NI device. Yeah, otherwise, yeah, because this is an example, so we just set as 1000. It really depends on your data collection. If you're downloading your signal from PhysioNet, then that sampling frequency should be in that description of the data set. Okay, let's move on. So in this example, the original signal is set as a 2 sinusoidal signal, one at 50 hertz, one at 120 hertz. I think you have seen this before. This should be a quite basic mathematic or like a sinusoidal function that you learn in your first year math class. That's the only thing that's defining the period of the sine function is this part 2 pi times 50. And if you divide this number by 2 pi, then you will get your period, which is 50. And similarly, you will get 120 here. And now we add one more white noise signal into this a perfect sinusoidal signal. Use a rand-n function here. You don't really need to understand all this part. I just know this is what we added in here. So we manually creating some noise. And if we done that, then we can plot this signal in the time domain. So if I comment all this and I run this, you will see this is the signal embedded with the white noise in time domain. This is the amplitude, and that's in time. And the unit is milliseconds. So now, after that, we do FFT. As I said, it's quite a simple function. We just called FFTX. But you should notice that when I run all of those, you have capital Y as your FFT of X. And if you even before you double click the Y, you can see it's 1 by 100, sorry, 1500 complex double. So this becomes a complex number. And if you double click, you can see it's actually a complex number in every, except for the first one, of course. For the rest of them, it's always a complex number. So in order to plot this, we need the modulus or the absolute value of this complex number. So we use P2 equals to absolute value Y divided by L. And since it's two-sided, so we only, it's a mirror image, so we only want half of the P2. And this corrects us with the index of the FFT. After that, we can define the frequency domain. using P1, and if we plot this part, which is the second figure, figure 2, we will see this is the FFT. This figure 2 is the FFT of this figure in time domain. So we can see a huge spike over here, around 50 hertz, and another big spike here around 120 hertz, which is kind of what we expected. And we can also see this noise here, which is created by our X, the random function creating the white noise. So the next step in this example, it shows that if we remove entirely the white noise, we can do the FFT again. And in that third figure, we can see there's no noise at all. And we have a beautiful huge spike here and another spike here. So this is how we do FFT. So we go back to our example here. Similarly, we can do uncomment this part. And first thing, we set our sampling frequency as 500. T is equal to 1 over Fs. As I said before, L is equal to the length, data sec1, and T is equal to L minus 1 times T. And we do FFT, and we do very similar things as the example showed us. So if I haven't really changed the title, so this is probably not a good example for this title here, but we just give it a run. Undefined function, seg1, or seg01, sorry. Probably I need to change a little bit more. So this is called data seg01. I need to change all the axes to that. Yeah, should be fine. Yeah, so this is what we have for apparently for this FFT. Looks somewhat weird, but I think it should be the case since it's from 0 to 250. I guess we just have to include a bit more samples in this data set 001. So when you do your FFT, it's a good start to read this first, to read this example first and follow what this example have done, and give a go on your own collected signal. See whether you have see whether you run into some warnings or error, and if you have any problem, you can always chat with us, give us a call. I mean here, so we can help you. All right.
Okay, thank you, Carrie. Maybe Jeff, you will give some explanation for use LabVIEW for the real-time implementation.
Yep.
Thank you, Jeff.
So I'll just share my screen. I'll just share LabVIEw.
You want to take the host?
I know, it's fine. I'm good.
Okay.
Okay. So share. So is everyone able to see my screen?
Yeah.
Yeah. So okay. So before we go, let's look into the basics of LabVIEW. So once you